Hey everyone, how's it going?
Hey everyone, how's it going?
Whoops, got some feedback there. That should be fixed now. Okay, so welcome to our session on stationary waves. So yeah, the way this will work is I'm going to go through I'm going to go through some stuff on stationary waves. And once we've done that, the session will be split into two parts. And at the end of each half, we'll do some exam questions to kind of practice and see if we understood what we learned so far. If you have any questions along the way, just type them in the chat. I might also ask you questions just to see if you're kind of understanding what's going on. So feel free to answer in the chat. Don't worry if you get anything wrong. It's more just for me to tell how the session's going and if there's anything I should go back over. But I think that's pretty much everything I want to say. So I think we should pretty much get started. So, like I said, I'll be keeping an eye on the chat. So ask me any questions you have, and let's get going. Seems a shame to move on from this really nice little picture, but let's do this. Okay, so about me, I'm Matt W. I'm the lead physics teacher here at SnapRevise. I'm also a PhD student at Oxford in kind of computer science and physics and a bit of maths. And I've been an A-level physics student for the last 6 years or so. I believe this is AS rather than A-level, yeah. Although we will just check when we look at the spec points. I'm not sure if we'll be able to tell actually. I can't remember for sure, but I think this is AS. Maybe someone in the chat knows. If someone knows, just let them know. Okay, a bit about us at SnapRevise as well. So we're doing a session today, but also we've got a lot of other stuff that's coming up. Yeah, so we are going to do some past paper questions today. Don't worry. We'll do some past paper questions in the middle and some past paper questions at the end. It is AS. Perfect. Okay. So in terms of what else we're doing at SnapRevise, we're soon going to be doing some other live stuff. We're going to be doing an A-level exam crash course. I'll mention it more at the end, so I'll just mention it briefly now. So essentially, this is a chance to go through various aspects that might help you out with your A-level exams or AS exams. So we kind of do, it's a day-long or 2-day-long thing, and you can come in person. It's going to be in Regent's University in London, or you can watch online from anywhere in the world. It's also going to be live streamed. Okay, so what are we going to do with it? We are going to start at the start of the day. We're going to go through exam technique, kind of learn how to extract what it is that the examiner actually wants us to answer. Sometimes it's not always clear what the question's actually about. And then we're going to practice that exam technique throughout the day, doing some of what we've identified to be some of the trickier topics or the topics people struggle with more. So if I remember correctly, in A-level, we're going to be looking a bit about magnetic fields and gravitational fields, but lots of other stuff as well. There's a kind of revision booklet that we make that you can take away at the end of the day. This is, in previous years, actually something people have really, really liked. And it will come away with it will have extra materials for you to practice with at home, past paper questions, etc., and a review of everything we did in the session. And throughout the day, I will be explaining stuff and going through past paper questions, but also if you're confused about anything, you'll be able to message one of our other tutors who are there following the sessions with us. And if you have any questions, you can message them. There'll be a big chat, and they'll be answering as I'm giving the session. So the session can keep moving, but you can ask any questions you're confused about. All right, so I'll mention more about that at the end, but for now, I think it's time for us to get started. So this is about stationary waves, and the objectives are to try and understand the concepts of phase and superposition. Then we're going to describe how stationary waves are actually formed, and we're going to define the nodes and harmonics of a stationary wave. So that last bit is some more language and some more maths actually for describing stationary waves. All right, let's do this. It's probably a good idea to review a couple of things before we get going. We're going to be using a lot of the language that physicists use to describe waves. So there's a few things we should probably fix. So just to get us warmed up, can anyone in the chat say what this displacement here is? The maximum displacement of a wave. We have a kind of a special word for that. What's that word? So on the SnapRevise website, we've definitely made videos on electricity. I'm not sure if there are any of those on YouTube or not. Okay, so this displacement here is the amplitude, and we'll give it the symbol A. Yeah, good, really nice, thanks. So we'll mention that a lot. If this was a diagram representing a kind of a photograph that you took of a wave in space, then the distance between two peaks, we would give it the symbol lambda, and we'll typically call that the wavelength. Okay. Yeah, good. The first one was amplitude. In general, at any part of the wave, we will call how far away it is from the equilibrium, which is the fancy word for the middle. So the middle is called the equilibrium. And we'll call how far we're displaced from the equilibrium. We'll usually give it something like the symbol X. Sometimes it's some other thing, but we'll give it the word displacement. Okay. Maybe the one other thing to mention is we have this symbol T, which represents the period of the wave. Can anyone say in the chat, if I know the period, how can I find the frequency of the wave? So the period is the, well, it's given the symbol T, and it's the time taken for one oscillation. Then there's the frequency, which is the number of oscillations per second. And you're absolutely right. Good. If you want to know the frequency, but what you actually know is the period, you just got to do 1 over the period, and that'll give you the frequency. Sweet. That'll come up later. Okay, so that's all the stuff you need to know to follow today's session. People were asking about if this is AS or A level. Someone said in the chat it was AS for at least one of the exam boards. Here's the specific spec points we're doing. So that might be handy for you. So there's the AQA ones. There's the OCR ones, and there's the LXL ones, which are always more concise. All right, let's get going. So we're going to start by discussing how it is that stationary waves are formed. And before we do that, we need to settle some new language. So a bit more language for how to describe waves. Let's start by talking about the word phase. So the phase of a point on a wave is a number used to describe where that point is in its oscillation. So that's kind of a funny phrase, where it is. What we mean by where it is it at the start of its oscillation? Is it at the end of its oscillation? Is it halfway through its oscillation? That's what we mean by where is it in its oscillation. Okay, so usually we'll say a wave, a point which is right at the start of its oscillation, like the one I've crossed out there, we'll usually call that being at a phase of 0. And we're going to find that we're going to measure phase in general, either using radians or degrees. So we'll come back to that in a second. But first of all, let's settle some other language. Sometimes we care about 2 points, like point A here and point B, say here. And then we could talk about the phase difference between these 2 points, and that is simply the difference between their phases. So no surprises there, but we need to get some numbers going soon, so we will do that. So let's do this now, actually. So one way to measure phase, one way to say how far through a cycle you are, is to say going all the way round to this point here would be 360 degrees. Going like all the way around your oscillation, it's like going all the way around a circle or something. So that's why we call that 360 degrees. So if that's 360 degrees, halfway would be 180. So what is the phase of B here? What's the phase of B? All the way to the end is 360. Halfway is 180. B looks like it's about a quarter of the way through the oscillation. So that's going to be 90 degrees. Perfect. So then the phase difference between A and B would be 90 degrees. That's the difference between their phases. The phase difference between B, and let's call this thing here, well, let's call this C and D. The phase difference between B and D would be, well, the difference between their phases. So 360 minus 90, which would be 270 degrees. So that's the difference between their phases. Good, absolutely right. So B was at a phase of 90. So if 2 points are at the same point of their oscillation, we would expect their phase difference to be 0, but that's not quite right. For instance, there's point A and point D. They're at the same point in their oscillation, just D is like a whole extra cycle through. So in general, the difference that's the phase difference, I mean, will be some number times 360, some whole number. There'll be some lump sum number of 360 degrees apart if they're at the same point in their oscillation. Now, one thing to mention is sometimes if you're familiar with radians, we would instead call 360 degrees 2 pi radians, in which case over here, 2 points at the same point in their oscillation would be some number of 2 pi radians apart. We won't be too worried about the difference between degrees and radians today. All right, good. Hopefully it's making sense so far. Do let me know if there are any questions. That's the language we're going to be using today. First kind of physical effect we're going to talk about is superposition. Okay, so when two waves meet, the resultant displacement of those two waves kind of combining together will be the vector sum of their displacements. Okay, so this is a physical effect. This is a physical rule, so let's see it in action. Let's imagine we have two waves here. For instance, we have wave A, which is moving to the right, and we have wave B here, which is moving to the left. At some point, these waves are going to bump into each other. Assuming they're going at the same velocity, they'll bump into each other in the middle here. Let's say that this first wave here has a displacement of A, has an amplitude of A, and this wave also has an amplitude of capital A. Then the rule says the displacement when they meet, so when they meet, they'll kind of crash into each other at the middle here. So there's two waves crashing into each other there. Their new displacement will be the vector sum of these displacements. So here they both point up, we add them together, and we'll get a bigger displacement. And that bigger displacement, that combined wave, will have an amplitude of, well, what will be the amplitude of this wave? We've got to add their displacements together. So if they've both got a displacement of A, what is the displacement of the combined wave? Yeah, absolutely right. It just doubles. It's going to be 2 lots of the amplitude. Perfect. Okay. So we just kind of saw this rule on the left here. When two peaks, that's what we had here, or two troughs meet, the resultant will be the resultant amplitude will be the sum of those amplitudes. Sum of amplitudes. Okay, let's see the opposite situation where we have one peak that's going to bump into one trough. And for simplicity, let's imagine that they both still have an amplitude A. Just one's going up, one's going down. When they meet in the middle, what will be the displacement? So when they meet, what will be the displacement here at the middle? One's going up with a displacement of A, one's going down with a displacement of A. Zero, good. It's the vector sum. So you don't just add the magnitudes, you add the directions. And when you add those two vectors together, 1A going up and 1A going down, you'll just get a vector of size 0. Good. So when a peak meets a trough, the resultant amplitude is given by the difference. Here, the difference was 0. If one was bigger than the other, then yeah. Yes, I am the teacher. I should know that's true. Okay, so now we're going to kind of build on this to look at another effect. So now we understand about superposition. We're going to see a kind of slightly more complicated situation where superposition causes quite a weird, at least kind of visual effect, or auditory if these were sound waves. So when we have two continuous coherent waves meeting and moving in opposite directions. So let's imagine, for instance, that the orange wave here is moving to the right. So the orange wave is moving to the right. And let's imagine that we have the pink, or is it maybe mauve wave here, moving to the left. Let's call it mauve. Okay. When you have these two waves and they're going in opposite directions and they have the same wavelength, that's what this coherent thing means here. Same wavelength, same speed. Then you'll get kind of a weird effect. Okay, so here's what's going to happen. Let's fix our attention on this point here. Okay. At the moment, roughly speaking, these two waves are working together, right? They're both trying to pull the wave upwards. Cool. Okay, so if we imagine the combination of these two waves, it's going to be some quite big kind of combined effect. Cool. Okay. There are other points in this wave at the moment where the two waves are essentially working against each other. So let's try and get a good example. Here, one wave is pulling up just as much as the other wave is pulling down. So as a result, the total displacement there would be 0. Now, what's weird is that as time goes on, this isn't really going to change. There are constant points of constructive interference, like this one here. This is constructive. And there are constant points of destructive interference, points where the waves act against each other. Okay, so let's see how this works. Well, imagine some time goes on. The orange wave moves to the right, and so the orange wave has the peak getting over here now. So the orange wave gets a bit higher, but also the pink wave is moving to the left. So this peak makes it over to the left. And so the pink wave is also going to be higher at this point. So as time goes on, these two waves still keep on working together. Sure, the displacement goes up even a bit higher, but it's still constructive interference. They're still always working together. Whereas if we look at this point of destructive interference, if the orange wave goes to the right, then at a later time, this lower bit of the wave will be here. So it'll be pulling up slightly less harder. But if the pink wave is moving to the left, then it's also going to have a kind of smaller amplitude bit of the wave here now, and they're still going to perfectly cancel. So when you have two waves going in opposite directions, you get this constant point where they're always canceling each other out, no matter what time. And you get these other points where they're always working together. Granted, they're going up and down still, so it's still going to oscillate up and down, but they're always working together. Okay, so the result here is you get some points, and there should be some more here. This one here, maybe this one here, roughly. Okay, this is constructive, so there'll be another destructive one here. You get constant points where there's never any displacement, and you get these other points between them where there's plenty of displacement. And that's why you get this picture that you'll see in the textbook, the kind of picture of a stationary wave. Okay, so now we're just going to write this out in words, because in the exam, often you'll be asked to explain all this stuff, but just in words. So let's have a go. So when two continuous coherent waves meet, there will be points which are always, we like to use this phrase, in phase. Or there are the other points which are always out of phase, or in the extreme case, in antiphase. Okay, cool. So the point is that these will be points of constant, always constructive or always destructive interference. So these will be points of constant constructive or destructive interference. So the point here is because you have these interference, my spelling's not so great. Okay, so the point is you have these constant points of destructive interference. And so you have these points which are fixed on the wave. They never move. They stay there. And that's why we call it a stationary wave. So, okay. Resultant wave appears fixed, not moving to left or right. It only seems to move up or down. As a result, we call this a stationary wave. Now, can I spell stationary? I think so. Yeah. There we go. Good. So hopefully that's making sense so far. Yeah, you should be able to watch this live stream. I believe all the live streams just stay up on the SnapRevise YouTube channel. Okay, so has anyone got any questions? How are we feeling? Is this straightforward? Chuck a 1 in the chat if it is, 2 if it's all right, 3 if you're confused. And either way, just let me know if you have any questions. Okay, we got some middles, we got some goods. All right. Well, okay, yeah, some more middles, some more goods. Sweet. All right, well, I will now take us through a couple of exam questions. Someone was asking if we could do some past paper questions, and we can. Okay, so here's the first one. Figure 4 represents a stationary wave formed on a steel string fixed at P and Q when it is plucked at its center. Okay, explain why a stationary wave is formed on the string. So we've kind of described how a stationary wave is formed. So I'm going to put everything I said on the previous slide essentially in this answer. We just need one more thing, which is to explain why on earth there would be, well, we know that stationary waves happen when there's 2 coherent waves going in opposite directions. We just need to explain why that's going to happen here. Someone plucks the string. Why are there suddenly 2 waves going in opposite directions? So that's the key thing. So we're going to start by explaining that. Plucking the string. So this is the key first mark, after which everything else we've already said. Plucking the string creates 2 waves which move towards P and Q. Okay, so imagine we kind of pluck this string in the center here. I'll try and draw a hand plucking it, but it's going to be scary. There we go. There we go. We pluck the string and that sends a wave off to the right, sends a wave off to the left. The key thing is these will be reflected. So these waves are reflected at P and Q and have the same wavelength and speed. They were created by the same pluck. They have the same wavelength and the same speed. So the same wavelength and speed. So as a result, this makes 2 coherent waves passing in opposite directions. And as we saw on the last slide, when you have two coherent waves passing in opposite directions, that gives you a stationary wave. So you needed to know two coherent waves will give you a stationary wave. You needed to explain why on earth those were going to be there. Good. Okay. So next question. When a note is played on a violin, the sound it produces consists of the fundamental and many overtones. We're going to explain what that means in the second half of the session. Okay, figure 8 shows the shape of the string for a stationary wave that corresponds to one of these overtones. So you can just think of an overtone for now as being some special stationary wave that you get on a string when you pluck it. Okay. Or when you play the violin, so when you bow it as well. Okay, the positions of the maximum and zero displacement for one overtone are shown. Okay, points A and B are fixed. Points X, Y, and Z are points on the string. Describe the motion of point X. Okay, so the key thing here is often when people think of waves moving around, they imagine that maybe the points could be moving to the left or right or something. That would be true for a longitudinal wave, but this is a transverse wave where the points kind of stay fixed and just go up and down. So the first thing they want to know about the motion of X here is they want to know that we know this point X is just going up and down. That's all that's actually happening here. So, okay, point X will constantly move up and down. And down. And let's just say some more things, just because we see there's 2 marks here. Maybe what else we can do is give some kind of reference. Any point to the left of it is going up and down with a bigger amplitude. It's got a bigger range of motion. Anything closer to the node here, this point that's stuck, will have a smaller amplitude. So it always has bigger amplitude than the points to its right. Whoops, 1 second. I just made a mistake there. There we go. And the points to its right. Aha, so the point is that a normal wave would look like it was going to the left, or it was look like it's going to the right. This thing is stationary in the sense that it only ever looks like it's going up or down. So it's only stationary like in the horizontal direction. It's still allowed to move up or down. It just won't look like it's going to the left or to the right. And it's because of that that we call it stationary. So maybe it's a slightly confusing name, but it's the one the physicists have landed on. Okay, now we're asked to state the phase relationship between X and Y and X and Z. We're actually going to start by looking at X and Z here. And we haven't really introduced this language yet, but there's 2 words you need to know. If 2 points are at the same point in their oscillation, we call them in phase. And X here, whatever point it is in its oscillation, Z is also at the same point. They're moving up and down together. It doesn't matter that Z's higher up. That just means it's oscillating with a higher amplitude. But the point is they're both at the same upwards point in their oscillation. So we would call X and Z as being in phase. We also have a word antiphase, and antiphase is what we mean when there's 180 degrees between one point and another. So in other words, when one point is at the maximum, the other point is at its minimum. And that's the relationship between X and Y here. X goes further and further up as Y goes further and further down. They're always at opposite points in their cycle. So we call that being in antiphase. phase. That's the word we have for that. So during destructive interference, the wave doesn't move left and doesn't move up and down. So due to the fact that there are constant points of constructive interference and destructive interference, the wave doesn't move left or right, but it does move up or down. Yeah. So it's the fact that there are some points that are always having destructive interference. That's this point here, this point here, this point here. Because of that, it can't go left or right. It has to go up or down. So because there are constant points of destructive interference, it's stationary. That's the idea. Good. Okay. So that's the exam questions for the first half. We'll look at some more, but first of all, let's introduce some more language and some more maths. And I think I secretly used some of these words already. So let's get them written down now. So if we have a stationary wave, a node is a point with always zero displacement. So a node is one of these places of constant destructive interference. So there's a node, there's a node, there's a node, and you get the point. It's these points that are never moving away from the origin. Okay. An antinode is the opposite. An antinode is a point that's, oh, I've lost my pen, is a point which always has the biggest displacement. The largest displacement on the string. Okay, so each of these points on the string is oscillating up and down, but there is one that is oscillating up and down with the biggest possible amplitude, and that's the one here. And we call that one an antinode. So there's an antinode, there's an antinode, there's an antinode, etc. Good, nice. So something to point out here is you can kind of maybe see from this diagram, it's kind of suggestive that the wavelength of this wave is this distance that I've just drawn out here. We'll talk about this more later, but notice that this distance, the kind of wavelength, if you were to track what looks like one of the actual waves here, is actually twice the distance between any two nodes here. Okay, so we'll talk more about that in just a second in more detail. So now we're going to introduce some even more language of harmonics. Okay, so we're going to specifically focus for now on the example we looked at in the previous exam question. And that example was this place where we took a string and we, for instance, plucked it or something to create two waves that went to the edges, reflected back on themselves to then make the stationary wave. So as a general kind of principle to keep in mind, a stationary wave is formed on a string when a progressive wave is reflected back on itself. Back on itself. So you might be wondering what this word progressive means. I don't know if we use this word yet. Don't worry too much about it. It just means a wave that is moving. So it just means not stationary. You have the idea of a stationary wave now. So the ones that are not stationary, the ones that actually look like they're moving, we're going to call them progressive. It's like they progress. So you have a pair of progressive waves that when they go together make one stationary wave. Good. Okay. Now, to create a stationary wave, something that we haven't talked about yet is you actually have to have just the right frequency. Okay, to create a stationary wave by plucking a string or by vibrating a string somehow, you need to have the right frequency. And we're going to see what those frequencies are. But first of all, they have special names. And the special name of a good frequency, a frequency that you can make a stationary wave at, is called a harmonic. So special frequencies where you can make stationary waves are called harmonics. So let's imagine that these x's at the end here represent the ends of our string. So this is one end of our string. This is another end of our string. Same here. In this picture, we have an end here and an end here. The thing in the middle, don't worry about for now. Okay, so we're going to see some of the pictures that kind of make sense on this diagram, and each picture that makes sense in a way that will kind of make more formal in a second will give you a harmonic. So let's see how this works. So the biggest looking stationary wave you could fit on a string is one where it's literally fixed either end of the string and just oscillates as one big lump in between. That's still stationary. It doesn't look like it's going left or it's going right. And that's the biggest one you can imagine fitting on the string. Because it's the biggest one, we call it the first one or the first harmonic. And it's actually easier to think about wavelengths rather than frequencies for now. So if you look at this, this looks like half of a wave. I could imagine trying to extend this picture out to make a whole wave. So it looks like the wave that I fitted on the string here, I've managed to fit half of the wavelength onto the string. So that's something that's allowed. You can have, let's say that this is the length of the string here. You're allowed to have the length of the string be half of the wavelength. That's a stationary wave you can make. Then there's the second harmonic. So harmonic, so the first harmonic is also called the fundamental harmonic or the fundamental frequency. Harmonic is just a special name for a frequency or a wavelength that you can fit on a string. That's it. Okay, so the second biggest one that you can fit, which is called the second harmonic. Here, what we've done is we've fitted a whole wavelength on the string. So here, the length of the string is the same as the wavelength. There's an even shorter wavelength that we could fit on the string, like this. So this time, we've got a wavelength, and then we've got another half of a wavelength. So altogether, we've got 3/2 of a wavelength being equal to the length of the string. No wave below fundamental, absolutely right. Many, many above, infinitely many above. This is the third harmonic. It's the third biggest picture you can fit on the string. Many, many above, infinitely above, but none below. Notice there's all these points here we've drawn in between. Remember, these are called the nodes. These are the places where there is no displacement happening. Okay, cool. So we'll cover a bit more of the maths used to describe these things. It kind of looks like a sine wave. I wouldn't know whether to say it is a sine wave or not exactly. Any equation that links lambda and harmonic, it tells you how many harmonics. Yeah, so I think you might be interested in the next page. So let's see if this answers your question. So, okay, a bit more words. Someone mentioned the fundamental frequency. The fundamental frequency of a string is the frequency of the first harmonic. So that's just a special name for the biggest, well, the smallest frequency, the biggest wavelength you can fit on the string. Good. Okay, cool. Now we have a formula for the frequency, the smallest frequency you can fit on a string, the frequency of the first harmonic, in terms of some material properties of a string. So this is a formula, and the formula says the smallest, the fundamental frequency that we just defined is 1/2 times the length of the string. So length of a string here times the tension in the string, the square root of, the tension in the string divided by this mu thing here, which is the mass per length of the string. So this is a formula that will let you, we'll see a couple more exam questions at the end. If I get a chance at the end, I'll go over phase difference a bit more. For now, I'll push through, but if we get some time at the end, I'll happily talk about it a bit more. Okay, cool. And we'll see some more exam questions in a second. Okay, so this is a formula for the fundamental frequency. That is the frequency of the first harmonic. Good. Okay, so some other rules that are worth knowing. The frequencies of the other harmonics are whole number multiples of the fundamental frequency. So, for example, the second harmonic has a frequency given by 2 times this fundamental frequency. The nth harmonic has a frequency given by n times the frequency of the fundamental harmonic, the fundamental frequency. Also, we kind of saw before that the wavelength of the fundamental over 2 was equal to the length of our string. We have some more formulas like this we can use in general. So the wavelength of the second harmonic we actually saw in the previous picture was the length of the string. In general, the wavelength of the nth harmonic, there's a general formula for this. It is 2 times the length of the string over n. So for example, the wavelength of the second harmonic could have been calculated by saying it's 2 times L over, well, it's the second harmonic, so we choose n to be 2, and that would give us L. So that's how you can use that formula. Okay, so how are we feeling? We do have some more exam questions to go through as well. So we'll finish today by going through some exam questions. Then I'll mention a bit more about seminars and stuff. And then if there's time after that, I can field any more additional questions too. That's a good point. We didn't actually introduce the word overtone. Now, I've actually slightly forgotten if overtone has like a good physics definition. I think it probably does. I think it's the same. I think overtone is just another word for harmonic. I've actually forgotten if that's a technical definition or not. So this will go to the end of the hour pretty much, and then I will be doing another session on the SnapRevise website. Okay. So let's do some exam questions. Figure 4 here shows a side view of a string on a guitar. The string cannot move at either of the 2 bridges where it's vibrating. So it's fixed in place, just like we were saying before. When vibrating in its fundamental mode, the frequency of the sound produced is 108 hertz. So straight away, we have a symbol for that. That's the thing we called F0. So let's jot that down. F0 is equal to 108 hertz. Okay. Calculate the wavelength of the fundamental mode of vibration. So the length of the string here is 0.64 meters. So the question is, what is the fundamental wavelength? What is the biggest wavelength we can fit on the string? So the biggest wave would look like this. What is the wavelength of this wave? If the length of the string is 0.64. What is the wavelength of this wave? What is the wavelength of the first harmonic? So a hint here is that it looks like we've fitted half a wave onto this string. Good. So the fundamental mode, the fundamental harmonic, always has a wavelength of twice the length of the string. So here the length of the string was 0.64. So it's 2 times 0.64. Perfect. So that's 1.28. Yeah, it's super easy to get the factors of 2 mixed up. Nice. Okay. For a triple I. Calculate the speed of a progressive wave on this string. Well, the speed of any wave is given by the wavelength times the frequency. That's not something we introduced today, so this is just for a bit more practice, and I'll just write it here. Okay, so the wavelength we already said was 1.28 meters. The frequency we already said was 108 hertz. So we just have to multiply them together, and then that'll be 138.24, and that's going to be in meters per second. All right, good. So we have, there we go. So we have another question. And then let's see. So one sec, my mouse seems to go missing. There we go. Right. While tuning the guitar, so it's the same question. The guitarist produces an overtone that has a node of 0.16 meters from bridge A. On figure 5, sketch the stationary wave produced and label all nodes that are present. So it's hard for me to ask you about this one because it's a drawing thing. But they've told us that there's a node here. Now, there are actually lots of good answers to this, but I think the most sensible one is to imagine that that's where we fit half a wavelength in then. So then we would fit another full wavelength by here, another one here, and another one here. Why have I drawn 4? Well, we have 0.64 meters altogether, and that first gap was 0.16, and 4 lots of 0.16 will fit in 0.64. So that's the diagram we want to draw, and they wanted us to label all the nodes. So we will happily do that. There's one, there's another, and there is another. Oh, and there's one more. I nearly missed the one at the end. There you go. So there's all the nodes labeled. Okay, 4BII. Calculate the frequency of this overtone. Okay, so let's go back a bit. We drew some pictures. This was the picture for the first harmonic. This was the picture then for the second harmonic. We had this picture for the third harmonic. And you can probably see that the picture that we're dealing with now is the next one on. So it's going to be the fourth harmonic here. We've gone up, down, up, down. So if you want to know which harmonic you're on, you just need to know like how many half wavelengths you fitted. So here there's 1, 2, 3, 4 of them. So we're at the fourth harmonic. So fourth harmonic. And once you know that, you can use our formula. The frequency of the fourth harmonic is 4 lots of the fundamental frequency. That's the formula that we came up with here. Okay, so the frequency is 4 lots of the fundamental frequency. And then we can just jot this down. We were already told the fundamental was 108. So we just have 4 lots of 108. And 4 lots of 108 is 432 hertz. Okay, good. So hopefully that's all making sense. Feel free to drop any questions in the chat. I have some things to tell you about, some other SnapRevise stuff that we're doing. After that, I might have a chance to field some more questions. So for now, you should be able to understand the concepts of phase and superposition, describe how a stationary wave is formed, and define the nodes and harmonics of a stationary wave. All right, so hopefully that's making sense. Do let me know if you have any questions. Yeah, hopefully that was helpful. And now, I mentioned at the start about some of the other things that we're doing at SnapRevise. The thing that I'm really excited to talk about is the A-level exam crash courses. So we do these once a year, basically once we start approaching exam season. And I mentioned at the start, there was kind of 4 key things that we were doing, 4 key kind of parts of these crash courses, of these seminars. I'm just going to mention them all in more detail now. And yeah, absolutely no worries. Thanks for sticking around. Okay, so the kind of first session of the day, the first half of the morning is spent on exam technique. So you can come to these things in person if you're nearby London area, or you can watch these on live stream online from anywhere. Don't need to be local to where the crash course is. So we're going to start by going through exam technique in the morning. The physics ones are going to be 4th and 5th of April, I believe. We'll check that at the end. So we're going to start by talking about exam technique skills, specifically how to break down questions in the exams. Like, one of the difficulties that I think a lot of people find with exam questions is they know the stuff, but it's hard to figure out exactly what it is that the examiner is actually asking you for. Now, it turns out that there's actually quite a lot of kind of repeating structure in the way exam questions are written. So we're going to cover all the kind of ranges of question types that come up in the exam. And we'll talk about the kind of structure of an exam question here. So you can see us talking a bit, or the kind of thing that we'll talk about here. We'll split up exam questions into kind of the different parts to help us figure out what the examiner wants from us in each question. And we'll actually go through some examples where I will actually go through answering some of these questions and explain how I would think about them. Okay, so once we've practiced the exam technique, of course, one of the other big problems is that there is some stuff in A-level and AS physics, a lot of it maybe, which can be quite tricky. So we're going to try and find, we have found what we think are some of the most challenging areas of the course. And we'll be revising those concepts. And the key thing is we're going to, throughout, keep using the kind of system that we developed in the morning for extracting information from exam questions. So we'll learn some stuff, and then just like today, we'll go through some exam questions, but we'll practice the exam technique from the morning in particular. Good. So for example, in the A-level sessions, I know we're going through gravitational fields and magnetic fields somewhat. There's some other stuff as well. Lots of other stuff as well, and we'll get a chance to see that at the end. So, okay. Now, there's another aspect of this, which is there's a booklet that we built that goes along with the crash course. And actually, a lot of the feedback we've had is that this is one of the really useful parts of the crash course. So this is a revision guide, essentially. It's based on, and we'll take you through the seminar throughout the day. But it has a lot of take-home resources as well, things we won't do during the day, like mock exams that we've written and kind of shorter topic tests that we have also written. Okay. And then the final thing is I won't myself actually answer questions while I'm giving the seminar like I was here. Instead, we have other tutors on hand that you can send questions to. So I'll be going through the session, but any questions you have, you can ask as many as you like in this chat, and the tutors will in real time answer you while I'm giving the session. Okay, so hopefully that's all making sense. And if you are interested in this stuff, then if you want to come in person, it's at Regent's University London, or you can live stream it via Zoom. So when are the different sessions here? So the physics is 2nd and 3rd of April. So those are the ones that I will be doing, this one here and this one here. We are also doing maths, chemistry, and biology. As you can see, they're all happening between the start and the middle of April. Okay, so I have one or two more things to say about it. I'll just show you what the actual topics are that we're going to be going through. In the meantime, I will keep an eye on the chat though. So let's see. I think I saw some questions there. So issue in diffraction and gradients. I'm not sure I actually know what a diffraction gratings. I'm not sure if we're doing any diffraction grading sessions on YouTube at the moment. Whatever we're doing, hopefully should be lined up on the channel already, although I'm not sure. Okay, so I'm just going to take a second here and show you. So if you go onto the SnapRevise website, and in particular, if you go to snaprevise.co.uk/seminars, you can find out more about all of this. So let's just check that's come up. Yeah, that's working good. Okay. So if you go through here, you can see all the different seminars that we're actually doing. A bit more of a breakdown of the things I mentioned today. And let's see, there's the 4 of us doing the seminars. And if you want to see the physics ones, we have some more details here on the website. Okay, so there's 2 days. There's an A-level day and an AS day. So there's a year 12 day and a year 13 day. In person, 109 quid. Online, slightly cheaper, 99 quid. And if we look at these, you'll be able to see a bit more about what we're going through. So on the year 12 day, we'll do the exam technique in the morning. Then we're going to go through mechanics, forces, momentum, equilibria, waves, and electricity and circuits. Okay. I've never seen so many pictures of my face at once. There we go. And then here for the year 13 session, we're going to be going through further mechanics, gravitational electric fields, magnetic fields and electromagnetism, and particles and nuclear physics. And like I said, in each of these sessions here, in each of these, we'll be going through, we'll be practicing the exam technique that we learn in the morning as well. And at the end of each, there's a question and answer session too. Okay, so I think that's pretty much everything I have to say about that. Thanks so much, everyone who stuck around. And I hope today was useful. We do one of these pretty much every month on YouTube, so it'll be great to see you all at the next one. And I think that's everything to show you. Yeah. So let me just take a look at the chat and see if there's any more questions. Issuing the derivation of the formula of diffraction gratings. Yeah, I definitely won't have time to be able to go through that right now. We might be able to take that as advice for like what one of the next ones we do on YouTube is. That is kind of an awkward formula to derive. I actually always found the 2-slit interference one even harder actually. Although I think maybe diffraction grading is only for certain exam boards, is that right? But yeah, I don't think I'll manage to get through that right now, I'm afraid. Sorry about that. Was there any more questions about today, what we went through in today's session? Okay, it looks like I'm not seeing any more questions, and I am actually going to go do another session on the SnapRevise website right now. So I will go and do that because that starts in a couple of minutes. Yeah, absolutely no problem. Thanks very much for sticking around. Thanks very much for typing stuff in the chat. Really helps me to see how everyone's getting on. And yeah, cheers for sticking around in the end and making it a nice place to give a session. All right, yeah, cheers again, and catch you all at the next one. All right, bye.